We've seen revenue functions, cost functions, and profit functions that give you the revenue, cost, and profit per X units of a product produced and sold. So if you see a marginal revenue function or whatever, that just means the derivative. So a marginal is just a rate of change, and a rate of change is just a derivative. So really, marginals and derivatives are the same thing. So we're just going to dive in and do some examples. Okay, so what we're talking about is like a monopoly type situation where what they charge for the product, it can depend on a number of things, but we're always assuming, okay, they sell every unit they produce. And all these things depend on how many units they produce and sell, right? The revenue and the cost depends on that, and then the profit is determined from those things. Like that. Profit is just revenue minus cost. So revenue is the total amount of money you bring in, and then you subtract the amount of money it costs you. Okay, so you should know that formula. The revenue, if we're just keeping it simple, is you just take, okay, the number of units sold, which is X, and you multiply it by the price per unit. And we're assuming now that that price is fixed. So the number of units sold will depend on the selling price of the unit. So this is how kind of supply and demand work in a monopoly market. If the price goes up, you'll sell less, right? The supply and demand, which again we're just assuming are equal to keep it simple, will go down if you raise the price too much. So the marginal revenue is the same exact thing as just the derivative of the revenue function. So when you see that word marginal, just know that you're taking the derivative. And I mean, this is a Calc 1 class. You're probably taking the derivative of anything, no matter what. Example. So the total revenue for the sale of, we'll say, X iPhones is given by R of X equals 36X minus 0.01X squared dollars. So if you sell X iPhones, that's how much your revenue is going to be. We didn't say anything about the cost or the profit in this example. We're just going to mess around with marginal revenue. Easy, right? Compared to the derivatives we've done, that's an incredibly easy one. So again, when you see marginal, just think, okay, it's R prime. So R prime is what? Just 36 minus 0.02X. And then the units for that would just be like dollars per unit sold. So if X changes by 1, if you sell one more unit, the revenue is going to change by that much, whatever 36 minus 0.02 times 1 is. When 600 units are sold, all we mean when we say that is what is R prime of 600? And that's, you just punch that into your calculator. It's 36 minus 0.02 times 600, which is just 24. The way to think about this is just think of it as the change in revenue, the difference between selling 600 units versus 601 units. So just think of it as the revenue if you were to just sell one more. So the revenue, so since R prime of 600 is 24, the revenue you get from selling the 600 first unit is approximately $24. Repeat the process with 200. I'm sorry, 2000. So just R prime of 2000, that's easy. And you get 36 minus 0.02 times 2,000, which is negative 4. So let's think about this. Your marginal revenue is now negative, which means at some point the revenue is going to start to go down. The revenue will still be positive. You're not losing money, but it'll be less than it was before. So you still want as much revenue as possible, but since that rate of change is now negative, the revenue at some point is going to start decreasing. All right, so if we sell essentially too many units, the revenue starts to go down. It's fine. We still want to sell them, but the revenue is not going up anymore. And then just note that if you did R prime of 1800, that would be 0. So that's like a sweet spot. And we've seen that before. If the derivative is 0, that's a local max. So the local max of the revenue occurs right at 1800. That's easy to verify. Okay, and then the graph will confirm that, right? So this is the graph of an upside down parabola. Note if x is 0, if you produce 0 units, you're going to have 0 revenue. At some point over there by 4,000, notice that the revenue dips back to being negative. So just assume that the function would cut off there. So in other words, if we produce that many units, we'll just stop making revenue, and we would just stop making units at that point. We would never go past that because it starts becoming negative. So that wouldn't really appear in the graph of the function if I bothered to cut it off. But the graph just shows you that, yeah, right around 1800, that's when you're making the most revenue from if you sell 1800, exactly 1800 iPhones. Okay, so this is what we've been talking about, a monopoly market. We know exactly how much of our thing that the market is demanding, and that's exactly how many we make. So we make supply equal demand, and we just set X equal to whatever that number is. So more kind of realistically, if we charge too much for our product, less people are going to buy it. Right? If our thing's too expensive, less people are going to buy it. So that means if P is the price we charge for 1 unit, then the amount we produce, X, is actually a function of P. Now, we write that a little bit backwards in economics. We write it the other way around. So really, X is the thing, well, we can decide. We can decide how many to make, and we can decide how much to charge for it. So we just flip it around in economics and write it where P is a function of X. But you could think about it either way. The price is a function of how much we're selling, in a sense, because if we're not selling enough, we have to probably lower the price, right? So it's kind of a push and pull. So the reason we write it like this is just so we can have like demand lines and supply lines on the same set of axes, because supply and demand, right, are both kind of functions of X. And then we can just compare the two and find things like equilibrium points, which I think you've probably seen before. So don't let that throw you. It's just how you're going to see it. Okay, so just think about it like that. The price we charge per unit depends on how many units we want to produce. Okay, so here we have a price that literally depends on X, right? So you see what I mean? P is a function of the variable X. So we're thinking of the price we charge for 1 unit as being a function of how many units we produce. And it's 106 minus 0.1 times X. X is always the amount of units we're producing. Revenue, so think back to this. Revenue is just how many units you sell times the price for every unit, right? So it's X times this, right? X times P of X. So that's a little formula for you. Revenue is just, it's how many things you sold times how much you sold it for. So that's why, the revenue is a function, right? It's not a constant thing. It depends on how many you're producing and selling, as does the price in this case. Okay, so just a couple steps here. Just let's do the math. Let's find the revenue function. It's 106 minus 0.1x times x. So it's just 106x minus 0.1x squared. So in this case, I didn't just give you the revenue function. I gave you the price function, and then I asked you for the revenue function, and it's just P of x times x. Okay, so there's the word marginal, which you go derivative, right? So this is just r prime of 500. R prime is easy, right? That's child's play for us. It's just 106 minus 0.2x. So there's your marginal revenue function. And then for 500, just plug in 500. 106 minus 0.2 times 500 is just 6. So right at the point when we're selling 500 units, that number is positive, so our revenue is increasing at a rate of $6 per unit sold. So it's not exactly right, but since it's increasing at a rate of 6 there, we just say that, okay, the revenue from the sale of the 500 first unit is going to be about $6. To figure out exactly what that is, you don't need a derivative. You just do R of 501 minus R of 500. So you just take the total revenue from selling 501 and you subtract the total revenue from selling 500, and that gives you the exact revenue of the sale of the 500 first unit. This is just a quick way of approximating it based on just a rate of change right there. So revenue is good, so we might want to maximize it. And I showed you the graph of that with the last problem, where if you just look at the revenue function, these are all like upside down parabolas. So the max is going to be right at what we call the vertex of the parabola. And there are a couple different ways to find the vertex of parabola, but we know that a way to find the max of any function, right, is to take the derivative and set it equal to 0. So when the marginal revenue is 0, that means you're basically switching from the revenue per unit sold being increasing to that all of a sudden starts decreasing, right? So right at that sweet spot is the moment when you're making the most you're ever going to make on your product. It's when you're producing exactly that many. It's always instructive to look at a graph, and it can be hard to graph these things on your calculators that have these gigantic numbers in it because of the scale. So just embrace the little zoom fit button that usually works. So you can just look at it and say, okay, if I produce like 500 some units, right, that's when I'm going to be maximizing my revenue. Now that doesn't necessarily mean your profits are being maximized, because this doesn't take cost into account, right? Ultimately, like in the next example, we're going to maximize profit, which is the thing we would really want to do. Okay, so we can just see that, and you can use some functions on your calculator to find the max. You can trace, or there's actually a max function under calc. Or we can be smart and do math. Right? So the slope of the tangent line at the top, at the vertex of that thing is 0. So that means R prime is 0. And in this case, that's a very easy equation to solve. So you're just solving that equation. You can almost do it in your head. You move that over. You do 106 divided by 0.2, whatever that is. So it turns out to be 530 units, which is about what the graph looked like. Okay, so if we produce 530 units, kind of in this vacuum here, that's when we're going to make the most possible revenue. If we produce too many, we're going to make less. If we produce not enough, we're going to make less. If we produce either 0 or like 1,000, like around 1,500 it looks like, then we're not making anything, right? So we're making way too much at that point. Okay, so again, just picture the graph is cutting off there because it doesn't make any sense for revenue to be negative. And then I'm always going to ask you for like the other coordinate of the max. So remember, 530, if I ask you for the maximum revenue or the local max of a function in general, 530 isn't that. 530 is like where that happens. So you first find that by setting the derivative equal to 0 and solving it, but I'm always going to want you to plug that back in. So all I'm asking you for is the y coordinate of that vertex, right? If you already have this in the calculator, just do calc value 530 or whatever, or just plug this back into R. So it's you use R prime to find the x value of that sweet spot, and then you plug that number back into the original function. So R of 530 is $28,090. And if you look on the graph, yeah, that looks right. It's pretty close to 30,000. Okay, so that's the thing I really want. What is the maximum revenue? What's the most revenue we can rake in here? Okay, so in a non-monopoly market, in a competitive market, you're gonna basically have a price that you have to sell your product for to remain competitive. Right? You can't be selling the same thing as a store across town for $100 more. Nobody's going to go to you. They're going to go to the store across town. So in my example, we've determined that we have to sell our product, whatever it is, for 220 bucks. Okay, so if we produce X units per month, that total cost is going to be 60 plus 0.2 times X. So just imagine 60 is a fixed cost. So 60 is just the cost of maintaining the machine that we use to make the units, and electricity and whatever else. And then it's plus 0.2 times every unit we produce. So every single time we produce a unit, it's going to cost us, well, if it's dollars, it's going to, I guess, essentially cost us 20 cents. Because if you produce 1 unit, it's going to be 60.2. That's going to be the cost. If we produce 2 units, it's going to be 60.4. So it only costs us 20 cents to produce a unit, and we have $60 of fixed cost. So that's our cost function. We're going to use this information. It doesn't seem like we have enough info here, but we do have the cost function, the revenue function, and therefore the profit function. And then we're going to look at the marginal profit function, which is the thing we're really interested in, because that tells you how our profits are increasing and decreasing. Okay, so the cost and the revenue are given by the stuff we already have in front of us. We have the cost of producing a unit, which is based on how many we produce in a month, is 60 plus 0.2x, right? So if we make 10 units, it's going to cost, what, $62 to produce each one, right? So the more we make, it costs a little bit more to produce each unit. So if we make X units in a month, we just multiply X by that, by the cost of making one. So the cost is the total cost, like for how many units we make. In this case, it's for a month. The time period will vary. Is just the cost per times how many units there are. So it's just 60 plus 0.2x times x, which we're going to clean up to 60x plus 0.2x squared. The revenue is kind of the same deal. We're charging the same exact amount per unit, right? So now our revenue doesn't slide around, or our price per unit doesn't slide around. So our price has to be $2.20. So the total revenue, ignoring cost now, is just the price, how much we charge for every unit times the units produced, which is just X. So it's just 220X. So the revenue is linear. It's just 220 times how many we produce in a month. And then, right, that's how we get profit. So first we get the cost and the revenue functions based on the information we were given. Profit is revenue minus cost. So let's clean that up. R of X minus C of X is 220X minus, the parentheses you need here, 60X plus 0.2X squared, which we can certainly simplify that. Gives you 160x minus 0.2x squared. Okay, so there's our profit function. Now notice a couple things. Our cost function was quadratic, right? So that sort of slid around, and there would have been like a local max there or something. Now we don't want to maximize cost. Well, there would have been actually a local min there. We want to minimize cost. And then our revenue is just linear, so our profit function turns out to be quadratic as well. And if you look at, so if you think about the graph of that, that's an upside down parabola, right? So there's a vertex, and that vertex represents the maximum profit, which is good. Notice also that it kind of has to be this way. If you think about C of 0, C of 0 is 0, meaning if we don't produce anything, it doesn't cost us any money. R of 0 is also 0, and that's how it should be, right? And then P of 0 better be 0 as well. So P, the graph of P starts here at the origin, makes 0 stuff, you make 0 profit, goes up, and then starts to come back down. So there's going to be another spot down the road where if we hit, we're actually making 0 profit again. The marginal profit, again, you know that word, that just means P prime. It's no fancier than that. So P prime, yeah, you can do in your head, it's 160 minus 0.4x. Okay, so there it is. Now that's a linear function. Think about P prime with a with a negative slope, which means it's a line that's going down, right? So it's not always positive. At some point it switches from positive to negative. So if your P prime is negative, that means your function is starting to decrease, which means your profit is starting to decrease. Now it's still not negative. You can't have negative profit, but it is going down. So you want to avoid that. So you want to again find the vertex of that parabola. You want to find the maximum profit. Again, just like triggers, when you see the word maximum in a Calc 1 class, you are setting the derivative equal to 0, right? Don't overcomplicate it. You're probably doing that anyways. So take P prime, 160 minus 0.4x, set it equal to 0, and find x. That's going to give you the x value of the vertex of that parabola, which is on the very top. Okay, you know, the math here isn't hard. 160 minus 0.4x equals 0 gives you x is 400. So we want to produce 400 units. That's the best we can do here. 400 units is going to give us our maximum possible profit. And then when I say the maximum profit, don't skip that step because that's really easy. Just stick x equals 400 back into P. So the actual profit is 160 times 400 minus 0.2 times 400 squared. And that's just calculator stuff, so that's 32,000 bucks. So we did a lot there, just from the cost of producing 1 unit and the selling price for the unit. We got the maximum profit we can possibly make, right? Which turns out you want to make 400 units, and if you do that, you're going to make 32,000 bucks. Not bad.